we're going to be talking about Ohm's law, and during the fall and spring it might be a 2-week semester experiment, okay? But before we get started, I just want to mention about resistors. They have these really cool color bands. Let me show you. Can you see the color bands on that resistor? Right there. And then over here there's another resistor with color bands. So the color bands on the resistor, the very last color band is typically going to be silver or gold, and those address the tolerance value of, you make this resistor, and if it's supposed to have so many ohms, plus or minus how many. It's almost like the uncertainty in the resistor value itself. And we call it a tolerance here because when you're manufacturing these, you can't get it right on, say 10 ohms, but it might have a 5% tolerance or a 10% tolerance. And the better the tolerance, the more expensive the resistor probably is. There's 3 color bands, and each color helps you decide the value of the resistance. So this is just kind of neat. I'd like you to know this. Maybe you've never seen a resistor before, and the color bands, it's kind of nice to know that they do represent something besides just a pretty resistor. So let's do an example here. Well, here's 2,500 ohms, 250,000 ohms, excuse me. So the first band is a 2, and so we look at red and we find out that it's a 2, so we write 2 there. And then the second band is green, and that's a 5, so we write a 5 next. And the third band tells us how many zeros we place. And so we look at the third band is yellow, and that's 4. Okay, and so we put on 4 zeros, which means 250,000. So let's try another one. The 2 resistors on that circuit board that we looked at, there's a brown, black, and a brown. So if we look at the brown, it's a 1. And then if we look at the black, that's a 0. And then the last color is brown, 1. That means we add 1 more 0. So that one's 100 ohms. Okay? And then brown, green, brown, we do a 1. And then green is a 5. And then we're back to brown, which is a 1, so we add 1, 0, 150 ohms. Okay, so that's just a little tidbit about the color codes on resistors. Now, when I say the word resistance, what do you think of? Is this what you think of? Do you think of that indulgence property? I'm going to resist this chocolate cake. Just say no. Or is it yes? It looks like pretty good cake. Resistance is defined within Ohm's law. Ohm's law is a law that deals with electrical voltage potential, electrical current, and it deals with electrical resistance. And Ohm's law relates these 3 things together. So let's talk about them. The definition of Ohm's law is simply that the voltage divided by the resistance will equal the current. Okay, so V divided by R equals I. I is current, and I is measured in ampere, and V is voltage, and it's measured conveniently in volt. Ohm's law again, V divided by R equals I. Resistance is therefore defined as a volt per amp, and we give it the unit of ohm. Okay, and this is a capital Greek omega. Resistance is voltage divided by amps, or volts divided by current, if we state the names or if we state the units. There's an analogy that we can look at. We may have mentioned it in the resistivity lab, and that is the water analogy. When it comes to looking at Ohm's law, we can liken it to a water tower. In this example, again, we have Ohm's law, V divided by R equals I. We have a water tower here, and we call this the low voltage tower. And then we have a water tower over here, which we could call the high voltage tower. So in this water analogy, the height of the water is analogous to the voltage potential. Okay, this is going to add more pressure, if you will, to the water than this lower tower. So the higher the voltage, a 9-volt battery is going to have more voltage potential than a AA battery, which is 1.5 volts. Okay, so you can think of those as, in this analogy, as a high tower versus a low tower. When we look at Ohm's law, voltage and current are related to one another in what way? From this equation, we see that they're directly related to one another. If I double the voltage, I should double the current. That's a direct proportion. And so if I increase the voltage over here compared to my lower tower, that increase in voltage should show an increase in current. And so here we have the current represented by the water flow. If we could measure current, we would put a little window in the hose, and we would count the number of water molecules that go by that window in a given second. Okay, and so we're measuring the water flow, and the water flowing is the current in this analogy. So with a high voltage tower, high voltage potential, we're going to have a lot more water coming out the hose than with a low voltage tower. We have less current or less water coming out of the hose. Now we could look at Ohm's law a different way, and that is dealing with the resistance. See, there's an inverse proportionality between the resistance and the current. If you remember back to the resistivity lab, resistivity taught us that when we have a larger cross-sectional area, we've increased the paths of conductivity, and therefore the resistivity was lower, and therefore the resistance was lower. So in this example, we have two voltage towers, two water towers, that are the same voltage potential, they're the same height. But in one case, we have a hose that is very large, okay, yielding less resistance. The larger the cross-sectional area, the lower the resistance. And if this number becomes lower, then the current goes up. So if we compare a hose of this size versus this size, we'll see that the smaller hose is going to have a smaller current. And the larger hose is going to have a larger current. In other words, the one with less resistance is going to have greater current. The one with more resistance is going to have less current, because these are inversely proportional to one another, the resistance and the current. Ohm's law I like to associate with two prepositions, and I'd like you to remember these prepositions. There is voltage and there is current, and we're going to associate a preposition with each one. I remember fondly my youth getting excited about electricity and studying it, and back then Radio Shack was the place to go to find electronic parts, and you could buy books to study electronics, and you could buy all the little components and put them together and make things, make project kits. You could make a radio, or there was all sorts of things that I used to build. And I got so excited because I had saved my money and I bought a digital multimeter. This was just all the rage because it was digital. My dad had an analog multimeter which had this little needle which would go across to measure the different things, voltage and current. And this digital multimeter could measure voltage and current and resistance and even some other things that I didn't even know what they meant. And I remember getting that voltmeter home, that digital multimeter home, and I was so excited. I took it out and I hooked it up to a battery, a 9-volt battery, and I measured the voltage. And then I thought, I wonder what the voltage now don't do this, okay? But I wonder what the voltage is in the outlet, in the wall. So I took the voltmeter, and there was these two long metal probes and then some plastic handles, and I put them into the out. Don't do this, okay? But I put it into the outlet, and there it read. Okay, I could read the voltage. It was, whoa, the 9-volt battery is only 9 volts, but this was over 100 volts. And I was so impressed. And I thought, I wonder what the current is. Don't do this. Don't do this at home. So I switched the selector to current, and I took the two probes, and I put them in the socket, and I didn't know these two prepositions, how to separate voltage from current. And what happened was, the current went through the sensor, and those two metal probes went up in smoke with a big pop and a flash. So I put them in, and I was trying to read the current, and it was instantaneously turned into smoke. What was turned into smoke? Well, I pulled them out, and there were no probes left. My brand new digital multimeter just had plastic handles. Okay, so the two prepositions that we're going to try to associate. Voltage, we're going to associate with the word across. Okay? And current, we're going to associate with the word through. Those are the two prepositions we'll try to remember with regard to measuring voltage and measuring current. If we measured voltage across, that means that we have some resistor. That's the symbol for a resistor, by the way. If we wanted to measure the voltage across here, we would put our voltmeter right here, volts, and we would hook it across the resistor. We're trying to see what kind of voltage potential difference there is from one side to the other. The word current has the preposition through. In order to measure the current in this circuit, we would have to put the ammeter in series with the resistor. So we'd measure the current going through the wire. The voltage is measured across. Okay, and what was so dangerous about me measuring the current through the meter, okay, was that a wall outlet has, well, standard circuits are about 15 amps. Okay, and well, at 120 volts, 15 amps, that can kill you if you're not careful, because that amperage will go from one hand through your heart and then through the other hand. Now, I was holding insulated handles, and so I didn't get hurt, but I could have been. Incidentally, if you've ever watched a professional electrician, you'll find them doing something that might be considered by some as foolish, because they work on hot wires. They don't take the time to disconnect the circuit, and this is very dangerous to do. But the best electricians, if they're doing that, they might not be the, no, I'm kidding, but if they are doing that, you'll notice two things about how they stand. One is they're using one hand to do the work. They don't do work with two hands because they don't want to complete the circuit through their heart. The second thing you'll notice is they lean back. Okay, and that's so that if something happens to their balance, they're going to fall away from the work instead of falling into the work. And you can imagine crossing those wires across your chest. Okay, you don't want current to go through your body. All right, so remember, current is through and voltage is across. In this experiment, Ohm's law, we're going to be looking at a number of components. We're going to be looking at a resistor in different modes, by itself, in parallel, and in series. We'll get to that. We're going to talk about an inductor, which is a coil, and a capacitor, a diode, and then finally we're going to use a light bulb. Okay? And I have for you here the symbols used for these different components. So a resistor can look like this. Here's the standard symbol for a resistor. This is kind of the American version, but this is the international one. This, we have a coil, and that's just these half loops. Sometimes you'll see this as whole loops. And then here we have a capacitor, and then this is a diode, and these are really interesting. I think you'll enjoy studying all this, but especially the diode. And then the light bulb is kind of the bonus feature of this experiment. This might behave in a way that you're not expecting. But that's the symbol used for a light bulb. And by the way, just a little tidbit, these symbols you can get them in a number of websites. Here are two of them, kpsec.freeuk.com, and inside there is symbols. And you can see all the symbols here that pop up. So we can just scroll through and we can see lots, and there's a transformer, there's the ground symbol, motor, bell, inductors, switches, There's just all sorts of symbols. So there you can see the resistor symbol. And there's different kinds of resistors. There's a variable resistor called a rheostat, and there's a potentiometer, and then there's a preset variable resistor. And you've actually used all these things in your life. You just may not have known it. And then we have all the different types of capacitors. And so that's one of the websites. Kind of neat. And then the other one I just found, these are similar also, but they're vector drawings. So if you know anything about computer graphics, an SVG, a scalable vector graphic, you can make it huge and you don't lose the resolution. So here's a capacitor, and there's a number of electrical symbols here on this site. And this site is called clker.com. So we're going to be looking at these different components, and for each of these components, whether it's a resistor or a diode or a coil or a capacitor or a light bulb, we're going to be asking this question. Does this component obey Ohm's law? What do we mean? Does it have a choice? Can it disobey Ohm's law? Well, let's talk about what we mean by obey Ohm's law. We could say agree with Ohm's law. Remember, Ohm's law can be represented as V over R equals I, or we could rearrange the variables to show that a plot of V versus I has a slope of R. Okay, they're directly proportional to each other, so that constant of proportionality is the resistance R. When we plot V versus I, the slope would be the resistance. So which of these obeys Ohm's law? Well, to better answer that, we better look at Ohm's law simply as a function. That in this case we're plotting voltage versus current, so we'd say voltage equals resistance, the constant of proportionality, times I. So that looks like a function. A mathematical function is a map or a relationship that relates valid independent values on the x-axis to one and only one y value, dependent value. That's a function. So for every valid x value, you put that x value into your function, you're going to get only one y value. So let's use that definition of a function, knowing that Ohm's law is a function, and let's reevaluate each of these shapes. So again, we're plotting voltage versus current. Does this line satisfy a function? Yes. For every independent value, there is one and only one y value, dependent value. How about this line? That's a positive slope. This is a negative slope. Is this a function? Well, within this range, for every independent value, there's one and only one dependent value. We'll talk about this again in a minute. How about this one? For every independent value, there's only one dependent value. This is a function. How about this one? For this vertical line, we have one particular independent value along the x-axis. But for that one independent value, we have many, many, many dependent values. So this line does not the vertical line does not satisfy a function. So we'd have to say this line does not obey Ohm's law. This one does obey Ohm's law. This one does obey Ohm's law. This one, well, we'll have to talk about that, but it is a function. The circle, does that obey Ohm's law? For a given, it's almost like the line, for a given independent value, in this case there are two dependent values. So we'd have to say that this circle does not obey Ohm's law. Now if we just looked at a portion of the circle, right here, isolated that portion of the circle, we could say that portion is obeying Ohm's law. What did we say the slope of voltage versus current represents? A volt per amp is an ohm. It represents the resistance. The slope of this line, is it greater than 0 or less than 0? Does it make sense to have a negative resistance? That might, by the way, be a post-lab question. Now, in order to keep things interesting, for this experiment, we're going to take some sort of circuit arrangement. It might be this one or something else where we have resistors and coils and capacitors and diodes and light bulbs. And we're going to put a current through each of these components. In other words, we're going to put a voltage across them. Remember those two prepositions? We could use a direct current. Okay? What that means is the current is flowing in one direction at all times. Or we could use what's called an alternating current. These are often referred to as DC and AC. What do we have in the wall? We have an AC circuit. What do you normally have in a battery? That's a DC, or a direct current. AC means that the current is flipping its direction. Yeah, current is a measurement of the flow of the charges. Current is a measure of the flow of the charges past a given point in a second, the ampere, but it also has associated with it a direction. Okay, so the current is either that way or that way. Which way do you think the charges are moving? Are they moving in the positive direction or the negative direction? Well, it turns out that Benjamin Franklin is the one who decided the direction of current flow, and he just had to guess, and so he said, I'm going to say that the current is flowing from the positive side to the negative side. And so he said that's the direction of positive current. He was wrong. It turns out that the charges are actually flowing from the negative to the positive. So today we're left with always calling current flow positive when the actual charges are flowing the other way. Okay. In order to change things up a little bit in this lab, we're not going to use a DC. We're not going to use a direct current. We're going to use an alternating current. And there's different waveforms. Here's some of the basic waveforms that you can encounter. There's a sine wave, okay, there's a square wave, there's a triangle wave, and then there's a sawtooth wave, which just goes down. And you can have modifications on these waves. You can combine them. There's all sorts of things you can do with AC waveforms. We are going to use the the triangle waveform, okay, which ramps up positive and then goes down through through 0 and then goes negative, and then it ramps up back to 0, and then it goes positive again, and then negative and positive. Okay, that's the waveform that we're going to put across each of these components. So that's the voltage pattern. We're going to use to create this a piece of equipment that's called a signal generator. It generates signals and in different waveforms, and we've chosen the triangle waveform. A couple warnings. First of all, watch out. The instructions in the lab manual and in some of the movies might talk about creating a new plot. You don't need to do that. There was a bug in the software and students were losing all their data for week 2. And so we've rectified that by making all the plots for you. And by that I mean we've established the vertical and the horizontal axes, voltage and current for most of these, but we do a change up later in the experiment. So whenever you see make this new plot, ignore that. Instead, just read the plot, see what's plotted, see what the units are, make sure you're aware. So remember that all plots are pre-made. Secondly, watch out. There is another bug in DataStudio, and it deals with something called temporary files that get written to the computer in a hidden way that are not seen by the user. And if there's a USB stick, a memory stick plugged into the computer, DataStudio can actually get confused, and it won't tell you that. It'll just start acting erratically, and you'll lose your data. It took many semesters for us to figure this out, and so now just the warning exists. Don't have a USB stick plugged into the computer when you're running DataStudio. When you're finished with the experiment, you're going to save or throughout the experiment, you're going to be saving it to the desktop. And then when you're done, you're going to quit DataStudio. So you're going you're going to quit DataStudio, and then you can just simply take your file and drag it to a USB stick that you plugged in later. So remember, watch out, don't have a USB stick plugged into your computer. So now begins the experiment. There'll be a separate movie for each component to talk through it. The purpose of this lab is to study Ohm's law, to experience different type of circuit components and see how they behave and what they might be used for. And thirdly, it's to experience DataStudio, to work with the software and the hardware and see how to control these things and understand them, how to read plots and interpret them. So there'll be a separate movie for each section, but the very next movie is just going to be simply, let's collect all the data in one sitting, and then we have time to just analyze everything. And if we needed to, we could go back and collect more data. But this will allow you to maybe work on this at home and at least have all the data so that you have consistent components from week 1 to week 2. By the end of the first week, you should have all your data collected. I like doing that right at the beginning of the experience. What did I just say? Take all the data at the beginning, okay? There's a video that shows you how to do that. Take all the data all at once on the right pages, okay, within the software. But at the end of the first class period, when this is a 2-week lab, you should have all the data taken, and your analysis should be up to about the coil or the capacitors, okay? So just kind of make that your goal for day 1. And then you'll have plenty of time to enjoy day 2 when we have this as a 2-week lab. Our intention in doing this over 2 weeks is to give you time to really not only just take the data and do the analysis, but to really think about these components, these circuit components, and how they might be used in different situations, and really to hopefully challenge you and for you and your lab partners to come up with new questions as you're looking at the data. We don't want you to just blaze through this and be done with it. We really want this to be a teaching time.